Hello, my name is Valter Uotila and this video demonstrates MultiCategory, a system that introduces applied category theory and functional programming into the field of multimodal database management systems. MultiCategory allows a user to unify and query multimodal data using category theory and functional programming. Before getting familiar with the system, it is good to recall something about category theory and multimodal databases. A category consists of objects and morphisms. Objects are often drawn as circles and morphisms as arrows. There are certain rules that allow us to compose morphisms. Category theory is useful for modeling and unifying different structures and defining structure-preserved mappings like functor in this picture. Multimodal databases are able to store and query heterogeneous data in different models and formats. There is a single unified backend that can store, for instance, relational data, property graph, JSON and XML documents, as well as relationships between these. Characteristical features for multimodal databases are a common query language, general index for all models, and ACID transactions. There are multiple motivations to apply category theory to multimodal databases. A category theory is a formal, precise, and high-quality framework to handle a variety of data on a logical level. It is simplifying and unifying theory that guarantees correctness of each action in a database. And previous research has applied category theory to data management very promising ways. In this demonstration, we are combining these two fields and demonstrating the ideas using functional programming. Our first demonstration shows how we have unified the graph, relational, and hierarchical models. In our work, we use category theory as a framework to model and unify different data models to create a theoretical foundation for a multimodal database. We have implemented multiple datasets into the system. The datasets have various tables, documents, and graphs following relational, XML, JSON, property graph, and RDF graph models. All of them are stored in a single Haskell backend. For each dataset, we have defined a schema category, which is a graph that presents a unified way to schema information and relationships of the data. Objects of the category are data types, and morphisms are typed functions between them. To keep the graph readable, compositions of morphisms are not visualized. For example, the user views the schema category of our simplest e-commerce dataset. The morphism called located connects the customer data type in the customer's graph with the location data type in the relational table. These connections are considered as morphisms of the category and they are visualized as edges. In our second demonstration, we show how to query multimodal data using the category theoretic constructions. For the chosen dataset, we have defined an example queries which are divided into groups with respect to the data models that they are following during query processing. We have defined a selective query language that is based on the idea behind Haskell fold function. Since fold function has a category theoretical definition, the core mechanism of the query processing is defined with category theory. The query language is a unified and cross-model language, and it works for all the models. Here the first query returns those customers who have credit limit more than 3,000. In the first line, we have defined a lambda function that describes how data points are mapped. Below that, the user sets the domain collection, which is a graph of customers. And on the last line, the user sets the model that the result data follows. Again, the nodes and edges reveal more information about the result. We can change the keyword after to get the result in different models. In the second example, the user queries those customers who have purchased a book. Also, location information from the locations table is included in the graph. This query combines graph, hierarchical, and relational models. Since orders are stored in XML, customers are stored in a graph, and locations are stored in a table. For more information, see our accompanying paper. Thank you.